Okay, this video is going to focus on molecular geometry and bonding theories. So you are going to first learn about the basics. You will learn about a central atom, a surrounding atom, and what do you mean by a type of molecule, and then we will introduce you to electron domain geometry, and then Lewis structure and molecular geometry based on Lewis structure. So let's go ahead and learn all these one by one. So first let's learn what do you mean by a central atom and what do you mean by a surrounding atom. Consider the figure given there. The molecule is C with 4 H around it. The C in the center we call as the central atom, and you can see that there are 4 hydrogens around it, and these hydrogens, because they are around the central atom, we call them as the surrounding atom. So we have 4 surrounding atoms for one central atom. The surrounding atom also has one more ring called as the electron domain. So that's what the name we'll be using, electron domain. So this compound has one C as the central atom, and it has got 4 hydrogens as the surrounding atom, and the name of the compound is methane. Now let's try to understand what are the different possible combination for the central atom with surrounding atom. So let's see what are the different shapes available. The first one is I can have one central atom with 2 electron domains, or I can have one central atom and 3 atoms surrounding it, or I can have one with 4. We do have more that will continue later. So now the electron domain is written over there. The first one is 2, the second one is 3, and the third one is 4. And the type of the molecule, we write it as the first one AB2. A represents the central atom, B2 represents the number of atoms surrounding it, and therefore the second one has one central atom and 3 electron domains, so we call the type as AB3. And the third one central atom and 4 atoms surrounding it, therefore it is AB4. So based on the type of the molecule, the electron domain geometry is predicted. An AB2 molecule is always called linear, and an AB3 is called trigonal planar, and AB4 is called tetrahedral. You need to learn these by heart, and one example for each one is given. A linear molecule is beryllium chloride, BeCl2, trigonal planar BF3, and tetrahedral is methane CH4. We'll go ahead and see about more type of molecules. Continuing from the previous phase, let's consider more possible combinations. So the other possible combinations are, I can have one central atom with 5 atoms surrounding it, or 5 electron domain, or I can have one central atom and 6 electron domain. So the electron domains are 5 and 6 in this case. So these are the type of the molecule will be AB5 and AB6, and the name of the molecules will be trigonal bipyramidal and octahedral, and then one example for each one of them is given, and you need to remember all these names because the previous one and this one, the electron domain geometry names, you need to remember them. Okay, in all these cases I said that I have a central atom and atoms are surrounding it. If the surrounding atoms are not all atoms, if you have a lone pair also, how will the name change? How will the shape change? Let's go ahead and learn about it. So continuing with it, we will learn if the surrounding atom is not only atoms, we have lone pairs also, how will the shape change? Consider 2 molecules. One we are going to consider is BH3, and then the other one ammonia, NH3. Looking at the 2 molecules, they look like an AB3 type molecule, hence the electron domain geometry should be trigonal planar for both. But is it really true? Let's write the Lewis structure and verify it. So the Lewis structure of BH3 is shown there. We have one boron surrounding with 3 hydrogens. So the electron domain geometry is 3 because we have 3 atoms surrounding the central atom B, and hence it is the AB3 type molecule and has the shape of, or electron domain geometry, trigonal planar. But in case of ammonia, when I write the Lewis structure, you see that I have 3 atoms and 1 lone pair on nitrogen. And hence the lone pair has to be counted, and this is an AB4 type of molecule and has a tetrahedral shape. So what do we conclude? Lone pairs have to be counted to get the type of molecule. And that's the reason ammonia with 1 lone pair and 3 atom is AB4. So don't just predict the electron geometry by looking at the molecule. A Lewis structure has to be written in order to predict the type of molecule and then the electron geometry. Here I have given you a chart of various electron geometry, and then depending on the number of lone pairs and the atoms surrounding it, we call it as bond pair, and the type of the molecule is also given, and then the electron domain geometry name is also given, and after that I have given a new name called molecular geometry. The electron domain geometry is the geometry which is predicted by the number of atoms or lone pairs surrounding it. Molecular geometry is depending on the lone pairs around it, the shape changes a little bit. The electrons, they repel the bonds, and therefore you get a different shape. The new shape is also given there, and an example for each one of them is given. So whenever they are asking you to predict the geometry, be clear and understand the question whether they are asking the electron domain geometry or molecular geometry. For example, I will start with when you have an electron domain of 3. When you don't have a lone pair and you have only 3 atoms surrounding it, the AB3 type molecule is called as trigonal planar, and even the molecular geometry is trigonal planar. But the moment it has 1 lone pair, look at it. It has the electron domain is 3 and it has 1 lone pair and 2 bonds. And the type is AB3, trigonal planar, but the molecular geometry becomes bent. So this is the difference between a molecular geometry and a trigonal electron domain geometry. Molecular geometry is the one which predicts the actual shape. One more example you can see with 2 lone pairs and electron domain of 4. It's a AB4 type of molecule. I have 2 lone pairs and 2 bonds, and then the electron domain geometry is tetrahedral, but the molecular geometry is bent. The example is water. So you can just go over the entire table and learn learning the electron domain geometry is easy. You have only 1, 2, 3, 4, 5 to learn. But molecular geometry, for the presence of lone pair, alters the shape, so you have to learn for each one of them. Especially you can see that when the electron domain is 5 and 6, we have 4 different shapes available. It's good that you learn all of them. So spend some 5 minutes each day looking at these and try remembering all these shapes. It's important. So let's just sum up what we have learned so far in one page. So you learned electron domain geometry. In order to predict the electron domain geometry, you need to count the bonds and the lone pairs. And then the type of the molecule, to predict the type of the molecule also, you need to count the bonds and lone pairs. Then what you need to predict, if you want to predict the molecular geometry, it can be different from electron domain because the molecular geometry depends on the number of lone pairs. And draw Lewis structures first before predicting the type of molecule and electron domain geometry. Let's predict the electron domain and the molecular geometry for some molecules. The first one is NCl3. So what is the first thing we do is we need to draw the Lewis structure. In order to draw the Lewis structure, we need to count the valence electron. Total valence electron is 5 from nitrogen and 3 times 7 from chlorine, so that is 26, and write the central atom and then the chlorine around it. So we have 3 atoms or 3 bond pairs, and then we need to find out how many lone electrons are on Cl. So 3 atoms or 2 bond pairs takes away 6 electrons, and lone electrons I have 6 and on 3 chlorine, therefore 18 electrons are gone. So total of 24. So out of 24, 26 minus 24, 2 electrons are left, hence you have 1 lone pair on nitrogen. Therefore, the type is AB4, and the electron domain geometry will be tetrahedral, and the molecular geometry, because of the presence of lone pair, it will change, and hence the molecular geometry is trigonal pyramidal. Let's predict the electron geometry for one more and molecular geometry for one more. Let's do H2S. As always, the first step you should do is to draw the Lewis structure. So counting the valence electrons, I get 2 from hydrogen and 6 from sulfur. Therefore, there are 8 valence electrons. So draw the skeleton structure, S in the central atom and H around it. So we have 2 atoms or 2 bond pairs, and then that means we have used up 4 electrons. And out of total of 8, 4 has been used up. Therefore, we are left with 4 electrons. Hence, we have 2 lone pairs on sulfur. So, looking at it, so we have 2 bonds and 2 lone pairs. Therefore, the type of the molecule will be AB4. So, look at it. Looking at H2S, you will think it is AB2, but actually it comes as AB4. And hence, the electron domain geometry is tetrahedral. And the molecular geometry, because of the presence of 2 lone pairs, it will be bent. One more example. The example we are considering now is XeF4. Looking at it, you will think it's a AB4 molecule, but let's see what it is. Let's do the Lewis structure. Counting on the valence electron, we have 36 valence electron, 8 from xenon and 28 from fluorine. The skeleton structure is given over there with all the lone pairs. So we have 4 atoms or 4 bond pairs, and then we have lone electrons on fluorine. So if you count all the electrons, so we have 8 electrons used up in bonds, and then we have 6 times 4, 24 electrons on fluorine, giving you a total of 32 electrons. So the number of electrons left is 4, 36 minus 32, and hence we have 2 lone pairs on xenon. So the type of the molecules, counting the lone pairs, 4 plus 2 is AB6. And hence the electron domain geometry, it comes as octahedral. So that's why never predicted just by looking at the molecule. The 2 lone pairs gives it an octahedral electron domain geometry. But the molecular geometry, presence of the lone pair, it distorts the octahedral and it's called square planar. So bottom line is, what you learn is, whenever you are asked to predict the electron domain geometry and the molecular geometry, never do it without drawing the Lewis structure. It's the Lewis structure which tells you the number of lone pairs, and the number of lone pair changes the type of molecule. So we'll go ahead and do a few more examples on this. So this video concludes here. I have another video in which more examples have been done.